These are the notes for Algebra 2, dealing with exponential growth and decay. Now, mostly what we're going to be sort of focusing in on are word problems. And when we're dealing with exponential growth and decay word problems, we really have a couple, or three different formulas that are going to show up. They're very similar formulas, and really it depends on which type of problem we're dealing with. So we're going to have some keywords that we're going to be looking out for as we work. Let's start with the exponential growth formula. Now, the exponential growth formula is for when a real life quantity increases by a fixed percent over every time period. So if something increases by 25% every year, that would be exponential growth, and we would use this exponential growth formula. I'm going to move this off to the side here. Now, we're going to look at the individual parts really quickly, and then look at some keywords that will show up if you're going to be asked to use the exponential growth formula. Because really, the hardest part of any of these problems is figuring out which of the formulas you need to use so you can set it up. So let's look at the individual bits. This y, right, the y equals, the y is the ending amount. So if I say after 27 years, how big is this population, I'm asking you for y. And for the moment, that's really all you're going to be asked to find is y. This a here, is the starting amount. And that will usually be given to you. You know, you'll start out with a certain population, or you'll start out with a certain value, amount of money, whatever, and you'll be asked how much it grows. R is the rate of increase, or the rate of change. Let's just call it the rate of change. So if something changes at a specific at a percentage, and I am going to put that down, percentage, that is R. Now it is going to be a percentage. All right, that is the kind of the thing about these exponential growth and decay problems, is that we're talking about growing by a percentage, not a fixed amount. So whatever the percentage is, that would be R. We would, of course, change it to a decimal when we're working with it. And T is, I'm going to say years, but of course it could be months, it could be days, whatever is specified. Now let's look at some keywords. We will end up using this particular formula if we're reading a problem and it has anything really that indicates an increase. Right? That's the obvious one. And sometimes the problem will say the population increases by this amount. It could, of course, also say that it grows, or grew, or will grow, etc. So that's another word. Exponential, let's see, what else could it be? It could just tell you the growth factor. It increases by a growth factor of whatever. And we'll see where that is. Now that is less likely, but it might still show up. Alright, so if we see anything that seems to imply growth, then we're going to automatically gravitate towards the exponential growth formula. Let's look at a situation here. Now, we see we have buffalo. In the last 12 years, so we have 12 years, an initial population of 38 buffalo. All right, that's a good key phrase there. An initial population, that's one of the parts of our formula. Grew by about 7% per year. Now notice, grew. That's that key word, right? Grew. It tells me that I'm going to be using an exponential growth formula, right? Because it grew. It didn't shrink. Right? It obviously didn't stay the same. It grew, so we use exponential growth. we want to first write an exponential model giving the number n of buffalo after t years, and then find out how many buffalo were in the park after 7 years. So, let's figure out some of our values. We're told the initial mount, A, is 38 buffalo. Right? We were straight up told that, the initial population of 38 buffalo. That's the way they're usually going to be. They're going to tell you an initial amount. The percent increase was 7% per year. But we want to change that to a decimal, and 7% is 0.07. So our model, n instead of y, n, equals a times 1 plus r to the t. We want to substitute in a and r because those are the values we were given. And we would get 38 times 1 plus 0.07 to the t. All right, we substituted in a and r. And we can simplify this. To simplify this, basically, we would add 1 and 0.07. So we get 38, 1 plus, or 1.07. I actually wasn't going to add there for a second. 1.07 to the t. Now this looks like an exponential growth function. We have an a is 38. We have a b is 1.07. And we have a variable t. Now notice that 1.07 is greater than 1, so it is a growth factor. Right? When we did the graphing, we saw that if we had an exponential growth function, we had a growth factor. So that should tell us that we're going to have an exponential growth function if nothing else did. And we can identify the growth factor. Now, we can use this model to figure out the number of buffalo when t equals 7. So that's what we're going to do. We're going to go to our calculators, and we're going to type it in. And we're literally just going to type it in exactly the way it's written. 38 times 1.07 to the 7th power gives us 61.02. So n equals 61.02, which is about 61 buffalo. And that's our answer. After 7 years, with an initial population of 38 buffalo, we would end up with 61 buffalo. All right, the compound interest formula is the next one we're going to look at. Now, it is related to the exponential growth formula. In fact, they look very similar. The difference between the exponential growth formula and the compound interest formula is this n. You can see this n here. Right, in the exponential growth formula, it was just 1 plus r. Now it's 1 plus r over n. And it was raised to the t power, but now it's raised to the n times t power. So again, let's look at some of the parts. We don't really need to worry so much about keywords in this case because every compound interest formula problem will involve money. So if there's money being put into an account for a certain amount of years, that is a compound interest problem. So instead of just regular keywords, we're just going to look at all the individual parts of this formula. We start with A, and it should come as no surprise that A is the ending amount. Now, another word for ending amount, particularly in compound interest formula problems, is the balance. So if we have a balance, that's the ending amount. P is the starting amount. Now, the reason why we use P instead of any other letters is because P stands for principal. And when we're dealing with money, we kind of want to use the money vocabulary. And in the real world, when we're dealing with bank accounts and stuff, or bills or whatever, the amount of money that we start with is our principal. So that is the term that we want to use. The starting amount is the principal. Of course, we have R. Put this way up here. R is still the rate of change, but in a compound interest problem, it's usually referred to as the interest rate. Right? Again, with a compound interest problem, we're usually going to use banker speak, right? The language they would use at a bank. Balance, principal, interest rate. Rate of change is interest rate. T is still, of course, years. Now we have this new letter here, N. And N, we don't have a fancy vocabulary word for it. It's the number of times interest is calculated. So the number of times interest is calculated is N. So if interest is calculated 3 times a year or 4 times a year or every day, whatever it happens to be, that's N. That's the number of time interest is calculated. And typically in one of these problems, you're going to be given a principal, an interest rate, a number of times interest is calculated, and a certain number of years, and you're going to be asked to find the balance. They're all going to be very much the same. So really, we know this formula. We're dealing with money. We're going to be using this formula. They're very straightforward problems. For instance, in this case, we deposit $2,900 in an account that pays 3.5% annual interest. We want to find the balance after 1 year if the interest is compounded monthly and annually. So now we have our principal, right? Our principal, P here. We have our interest rate, R. We have an amount of time, T. And then either one of these could be N. And we'll see that we're going to actually do 2 different problems. One where N is 12, because there are 12 months in a year. And one where N is 1, because annually means once per year. Let's start with the monthly. Now, monthly means that N is going to be 12. So we're going to substitute in P, R, N, and T using our compound interest formula. P is 2,900. It's already been put there for us. Now we have 1 plus R over N. Now R is 0.035. N is 12, so we have 0.035 over 12 to the 0.035 times 1. So I plugged in my numbers into that compound interest formula. Now I'm going to simplify it. I do not know what 0.035 over 12 is, so I need to figure that out first. So 0.035 divided by 12 is 0.0029. So I'm going to write 0.0029 in here. So 1 plus 0.0029 is 1.0029. Right? I just add these guys together. 0.035 times 1, that's easy. Right? That's just 0.035. And this I'll type into my calculator. So I'll have 2,900 times 1.0029 to the 0.035 power gives me very little, doesn't it? It gives me extremely little. Oh, I see I made a mistake here, didn't I? Because t should be 1, but I've substituted in r instead of n, didn't I? So n, these two should be the same. Well, that's not going to work at all, is it? So we're going to go back and we're going to change that. This should be 12, not 0.035. So let's go back and change that and make life a little bit easier. 2900 times 1.0029, all this stuff is the same. But instead of raising it to the 0.035 power, we're going to raise it to the 12th power. We should get an answer that makes a little bit more sense. And we do. We get $3,002.55. So $3,002.55. Yeah, you have to be real careful that you plug in things correctly because everyone can make that mistake. Let's try it again, but this time the interest is going to be compounded annually instead of monthly. So most everything is going to stay the same, but that n is going to be 1. So we're still going to have 1 plus 0.035 over 1 times 1 times 1 to the 1 times 1 power. This is a little bit easier to simplify. 0.035 over 1 is just 0.035. So when I simplify that, I get 1.035. 1 times 1 is 1, so it's to the first power. I will type that into my calculator. That simplifies a lot easier. We get 1.035 to the first power, which of course doesn't really do anything. And we get $3,001.50. $3,001.50. Right, that is my ending balance. Now, you'll notice I didn't accrue quite as much interest when it was compounded annually versus when I compounded it monthly. And that's going to hold. The more often you calculate interest, the more money you make. And so if we calculated interest every day, we'd end up with more money. Versus if we calculated interest every month or even every week. That's kind of nifty, and we're going to see how that changes a little bit later when we start talking about functions involving e. For now, though, we're just looking at these simpler compound interest problems. And they all work the same way. The last one we're going to look at here is the exponential decay formula. And what you should notice is the exponential decay formula is almost exactly like the exponential growth formula. In fact, the only difference between the exponential decay formula and the exponential growth formula is that instead of 1 plus r, we have 1 minus r. Other than that, they are identical. Right? So all of our stuff is going to be the same. We're still going to have a starting amount. We're still going to have, or an ending amount. That's an ending amount. We're still going to have an ending amount. We're still going to have a starting amount. We are still going to have a rate of change. And we are still going to have years. Right, so all of these are exactly the same. The only difference is that minus instead of the plus. Now, the question is, when do you know that you need to use minus instead of plus? So we have some key words. If the problem involves things like decrease, right? Population decreases. If it shrinks, right? If your population shrinks, right? Again, instead of growing, it's shrinking. If something depreciates, that word depreciates, right? As opposed to appreciate. Depreciate means it loses value. So if something depreciates or it loses value, that's a big sign that you're going to be using the exponential decay formula. Let's look at an example of that here. Now it tells me that a new television set costs $1,200. Rather expensive television set. I would not buy it. The value decreases, there's that word, it decreases by 21% each year. So we have a rate of change. This is our initial value. We have a rate of change. We want to write an exponential decay model. Then estimate the value after 2 years. All right? And let's get this done. We are not using the graph to estimate anything, so you can ignore that part. The initial value was $1,200. The percent decrease is 21%, and of course we want to change that to a decimal, so that's 0.21. So the model would be 1,200. Again, A is 1,200. 1 minus 0.21 to the t. We substituted in A and R. We simplify it by subtracting. Now you can subtract this in a calculator. I will subtract it by knowing that 1 minus 0.21 is 0.79. So 0.79 is B, and again it's less than 1, so it is a decay factor. When t equals 2, what's the value of the television? Well, we type this in, and that's what we're going to do. We're going to go to our calculator, we're going to type in 1,200 times 0.79 to the second power, because t is 2. So after 2 years, the value of the TV is now $748.92. $748.92. That is a big drop off in value over 2 years.